IIR filter realization using direct form. The direct form 1 structure has the following properties. It can be regarded as two-zero filter section followed in a series by two-pole filter section. In most fixed point arithmetic schemes, the most commonly used, there is no possibility of internal filter overflow. That is, since there is a fundamentally only one summation point in the filter, and since fixed point overflow naturally wraps around from the largest positive to the largest negative number and vice versa, then as long as the final result is in range, overflow is avoided. Even when there is an overflow of intermediate result in the sum, this is an important, valuable, unusual property of DF1 filter structure. There are twice as many delays as are necessary. As a result, this structure is not canonical with respect to delay. In general, it is always possible to implement nth order filter using only n delay element. As in this case, with all direct form filter structure, the filter poles and zeros can vary sensitive to round off errors in the filter coefficient. This is usually not a problem for simple second order section, but it can become a problem for higher order direct form filters. This is the same numerical sensitivity that polynomial roots have with respect to polynomial coefficient round off. The sensitivity tends to be larger when the roots are clustered closely together. To minimize this sensitivity, it is common to factor a filter transfer function into series and parallel second order sections. It is very useful property of direct form 1 implementation that it cannot overflow internally in 2's complement fixed point arithmetic. As long as the output signal is in range, the filter will be free of numerical overflow. Most IR filter implementations do not have this property. While DF1 immune to internal overflow, it should not be concluded that it is always the best choice of implementation. A straightforward approach for IR filter realization is direct form 1, where the difference equation is evaluated directly. This form is practical for small filters but may be inefficient and impractical for complex design. So this form requires 2 n delay elements for a filter of order n. The difference equation for the second order DF2 structure is given by Vn and Yn, which can be interpreted as a two-pole filter followed in a series by two-zero filter. So n In the case of infinite precision numerical computations, the DF2 structure has the following properties. It can be regarded as a two-pole filter section followed by two-zero filter section. It is canonical with respect to delay. This happens because delay elements associated with the two-pole and two-zero sections are shared. In fixed point arithmetic, overflow can occur at the delay line input, unlike in a DF1 implementation. As with all direct form filter structure, the poles and zeros are sensitive to round off. error in the coefficient a1 and b1, especially for high transfer function order. Lower sensitivity is obtained using series low order sections. Since the poles come first in DF2 realization of an IR filter, the signal entering the state delay line typically require a large dynamic range than the output signal. In other words, it is common for the feedback portion of the DF2 IR filter to provide a large signal boost, which is then compensated by attenuation in the feed forward portion. As a result, if the input dynamic range is to remain unrestricted, the two delay elements may need to be implemented with high order guard bits to accommodate an extended dynamic range. If the number of bits in the delay element is doubled, then the benefit of having the number of delay relative to the DF1 structure is approximately cancelled. That is, the DF2 structure, which is canonical with respect to delay, may require just as much or more memory as the DF1 structure, even though the DF1 uses twice as many addressable delay elements. The disadvantage is that direct form 2 increases the possibility of arithmetic overflow for the filters of high Q or the resonance. It has been shown that as Q increases, the round of noise of both direct form topologies increases without bounds. This is because conceptually the signal is first passed through a all pole filter before the result of that is saturated, then passed an all zero filter. So these two are the diagrams for direct form 1 and direct form 2. Next is cascade form structure for IR system. In cascade form, the stages are cascaded or connected in a series. The output of one system is input to the another system. The total k number of stages are cascaded. The total system function h is given by h is equal to h1z dot h2z dot hkz. H is equal to y1z by x1z dot y2z by x2z dot ykz by xkz. H is equal to h1 h2 hkz. H is equal to, these two are the equations. So here h1z h2z dot hkz, these all are connected in cascade, that is series form. Input is x of n, that is x1 of n. Output of hz is y1 of n, and input to the h2 of z is x2n. This is cascade form realization of IR filter. Each h1z, h2z, etc. is a second order section and it is realized by the direct form. The system function for IR system is given by h of z is equal to summation k equal to 0 to m, and by expanding the above terms we get hz is equal to h1 h2z hkz, where hkz is bk0 bk1 z raised to minus 1 bk2 z raised to minus 2 dot. The parallel form structure for IR system. The system function for the IR system is given by this equation. The above system function can be expanded in parallel fraction by hz equal to c plus h1z plus h2z dot hkz, where c is a constant and hkz is nothing but bk0 plus bk1 z raised to minus 1 by 1 plus ak1 z raised to minus 1 ak2 z raised to minus 2. So this is the parallel form realization of IIR system. Here C is constant. Next is finite word length in IIR. Now regardless of the type of the implementation, the numbers processed by the digital system are ultimately stored in the register with finite capacity. Therefore, all digital networks operate with only finite number of binary digits, thus resulting in an inherent limitation on accuracy and processing. We know that the computer store numbers not with infinite precision but rather in some approximation that can be packed into a fixed number of bits or bytes, because of which we are losing some information. So the effect of losing this information on the response of digital filter. This effect we call finite word length effect. There are number of effects of finite word length effect like overflow error in addition, round off error in multiplication, effect of coefficient quantization, limit cycle, etc. These A number in a fixed point representation is exact. The arithmetic between the numbers in the fixed point representation is also exact with the condition. The first one answer is not outside the range, and the second one is the division is interpreted as producing an integer result. In floating point representation, a number is represented internally by a sign bit, an exact integer component e, and an exact positive integer m. In the realization of FIR and IR filter, hardware or in software on a general purpose computer, the accuracy with which the filter coefficient can be specified is limited by a word length of the computer. Since the coefficient used in implementing a given filter are not exact, the poles and zeros of the system function will be different from the desired poles and zeros. Consequently, we obtain a filter having a frequency response that is different from the frequency response of the filter with unquantized coefficients. Also, it sometimes affects stability of the filter. When signal is sampled or calculation in a computer is performed, the result must be placed in a register or memory location of fixed bit length. Rounding the values to the required size introduces an error in the sampling or calculation equal to the value of the lost bits, creating a nonlinear effect. Round off error is a characteristic of computer hardware. There is another different kind of error that is characteristic of program or algorithm use dependent of the hardware on which the program is executed. Many numerical algorithms compute a discrete approximation to some desired continuous quantity. For example, is an integral is evaluated numerically by computing a function at a discrete set of points rather than at every point. A function may be evaluated by summing a finite number of leading terms in its infinite series rather than all infinity terms. Overflow in addition of two or more binary numbers occurs when sum exceeds the word size available in the digital implementation of the system. limit cycle. Since the quantization inherent in finite precision arithmetic operation, the system nonlinear in recursive system, these nonlinearities often cause a periodic oscillation to occur in the output even when the input sequence is 0 or some non-zero value. When the parameter of rational system function or corresponding difference equation are quantized, the poles and zeros of the system move to the new position in the z-plane. Equivalently, the frequency response is from the original value. The cascade and the parallel form system function is consist of second order direct form system. In both the cases, each pair of complex conjugate poles pair is realized independently of all other poles. Thus, the error in particular pole pair is dependent of its distance from the other poles of the system function. The type of implementation, the number processed by the digital system are ultimately stored in memory register with finite capacity, so all digital network operate with only a finite number of binary digits, so resulting in an inherent limitation on accuracy of processing. Thank you.